Hello and welcome to the screencast on the properties of logarithms. Logarithms arise as inverses of exponential functions. In addition, we have motivated their development by our desire to solve exponential equations such as e to the k equals 3 for k. Because of the inverse relationship between exponential and logarithmic functions, there are several important properties of logarithms that are analogous to ones held by exponential functions. We will work to develop these properties in this video. Let's begin by first developing the logarithm of products property. Let a and b be any positive real numbers so that x equals log base 10 of a and y equals log base 10 of b. We can rewrite these two equations using the definition of the base 10 logarithm so that a equals 10 to the x and b equals 10 to the y. Using substitution, we can now say that log base 10 of a times b is going to equal log base 10 of 10 to the x times 10 to the y. And by exponent rules, we know that log base 10 of 10 to the x times 10 to the y equals log base 10 of 10 to the power of the quantity x plus y. And because the base 10 logarithm and powers of 10 function are inverses, we can simplify to log base 10 of 10 raised to the power of x plus y equals x plus y. In other words, we can say that log base 10 of a times b equals x plus y. And finally, recalling that x equals log base 10 of a and y equals log base 10 of b, we have shown that log base 10 of a times b equals log base 10 of a plus log base 10 of b. And this is true for any choice of positive real numbers a and b. Similar reasoning also shows the same property holds for logarithms of any base. For example, it is also true that the natural logarithm of a times b equals the natural logarithm of a plus the natural logarithm of b. Using nearly the same argument, a similar property holds for logarithms of a quotient. Again, let a and b be any positive real numbers so that x equals, well this time, natural log of a and y equals natural log of b. Then we can rewrite these two in exponential form as a equals e to the x and b equals e to the y. Then we can say that the natural log of the quantity a divided by b equals the natural log of e to the x divided by e to the y. Using properties of exponents, we know that the natural log of e to the x divided by e to the y equals the natural log of e raised to the quantity x minus y. And since the natural logarithm and the natural exponential function are inverses, we can conclude that the natural log of e raised to the quantity x minus y equals x minus y. So putting the last few steps together, we can say that the natural log of a divided by b equals x minus y. And lastly, recall that x equals the natural log of a and y equals the natural log of b. So we really have the natural log of a divided by b equals the natural log of a minus the natural log of b. Again, similar reasoning would show that the same property holds for logarithms of any base, not just the natural logarithm. Because positive integer exponents are a shorthand way to express repeated multiplication, we can use the logarithms for products property to think about exponents as well. For example, the natural log of a to the fourth equals the natural log of a times a times a times a. And by repeated application of the rule for the natural logarithm of a product, we see that the natural log of a to the fourth equals the natural log of a plus the natural log of a plus the natural log of a plus the natural log of a, which equals 4 natural log of a. A similar, more sophisticated argument works to show that for every real number t, the natural log of a raised to the t power equals t times the natural log of a. So in conclusion, we now have three new properties of logarithms. Namely, for any real number t and positive real numbers a and b, the natural log of a times b equals the natural log of a plus the natural log of b. The natural log of the quantity a divided by b equals the natural log of a minus the natural log of b. And the natural log of the quantity a raised to the t power equals t times the natural log of a. The rule that the natural log of the quantity a to the t power equals t times the natural log of a is extremely powerful. By working with logarithms appropriately, it enables us to move from having a variable in any exponential expression to the variable being part of a linear expression. Moreover, it enables us to solve exponential equations exactly, regardless of the base involved. In a future video, we will practice using this rule to do just that.